Today I'm going to take the topic of explainable AI in data mining. So the idea is that we have to make black box transparent. I'll explain what the black box actually, why we call it the black box. So let us go to the next slide, which is we are introducing the opacity problem in modern data mining. So modern machine learning algorithms can actually identify subtle patterns and make predictions with remarkable accuracy. Often they actually surpass human capabilities too. But this power comes with a significant trade-off. As our models grow more sophisticated, they become increasingly opaque. This is what the black box problem is. So when complex neural networks, so you have a complex neural networks, it has a billions and millions of parameters. Now it has billions though, which if you consider chatbots and all, there's billions. So they take make a very critical decision. How do you actually understand why it made up a specific choice? For example, you have approving a loan, diagnosing a medical condition. It is a very critical system for flagging fraudulent transactions. So we understand if it's approving a loan or if it is saying this medical condition doesn't happen or it is saying this particular transaction is fraudulent. How do we understand that why exactly why did we make that specific choice? So this is where I'm going to this is black box. This is the machine learning model. Why do we exactly call it the black box? Here you have it. So first you have an input and it gives an output, but you don't really know what is going on inside. It is completely opaque. You can't see through it. That is why it is called the black box or the opaque box problem. Next we have this thing. Now what exactly is explainable AI? So explainable AI is a tool that is designed to make AI systems more transparent and interpretable to humans. So rather than accepting outputs at a face value, it allows us to peek inside the algorithmic decision making process. We can understand the reasoning behind predictions and verify whether the model is functioning as intended. So you can think of XAI as providing a translator between the mathematical language of algorithms and the conceptual language of humans. You have various equations, you have things like entropies, you have neural networks calculation. So this is being translated into simple graphs and numbers, which can be understood by humans. So this is what XAI does. So why XAI matters more than ever in data mining? The first thing is transparency for stakeholder confidence. Next, we have for trust, maintaining and building trust. Third one is fairness and unbiased decision. Next, regulatory compliance like model debugging and improvement and scientific discovery. So these are what XAI does. This is what XAI does as whole. Next, we have the XAI toolbox. So there are two types of XAI models. First one is called model specific approaches. So and the other one is model agnostic approaches. So I'll tell you the two. The first one is model specific approach. It has built-in interpretabilities. So I'll give you an example. So first one is a decision tree. So in decision tree, each node represents a question about your data with branches representing the possible answers. So here you have, so if the outlook is sunny and humidity is normal, will I go out and play? Let us see. So outlook is sunny and the humidity is normal. So yes, I will go out to play. But what if it is raining and the wind is very strong? Will I go out? No. This is how. So as you can see, while looking at the decision tree, I can just say that I can just take the decision completely. We can understand why a particular decision is being taken. But uh, next, decision is being taken. So similarly, we have rule-based systems. So you have if you say if income is so if a particular person's income is greater than $60,000 and the credit score is greater than 700 and his debt ratio is less than 0.3, you can just approve his loan. We can understand from here why it is being why a particular this particular person's is being approved or not approved in a rule-based system. Next come linear models. So basically this is logistic regression or linear regression. So here's the code. We are defining a linear regression, we're declaring a linear regression model. We are fitting, we are storing the coefficients and we are printing the coefficients. And you have here. So from this, without even knowing the data, without even understanding anything, we can just say that so a particular decision. So over here, income is very important. Next, credit score comes next, and you as employed it comes next. It is not very insignificant, but it is the least important of all. So here, this is how we interpret from a linear regression model. This is how in the interpretability. But we go to the next one, which for we have neural networks, for example. You don't know how you have a very complex neural networks. If you have billions of parameters, you have millions of parameters, so you can't really say, it's not really built in. Interpretability is not really built in. It's really hard to say how particular answer came from, or the output came from the model. So even the same thing even happens to less complex models, even gradient boosting methods or ensemble methods. It's really hard to tell. It's really hard to interpret the answer. So these are actually proper black box models. So these actually have great and superior performance compared to decision tree or linear regression, but they have a very bad interpretability. So this is where these two come into the clutch: Lime and Sharp. So LIME is short for local interpretable model agnostic explanations. So I'll tell you how it works in the next slide actually. So here you have, so you build a black box model. So let us consider a neural network over here. Then you just generate random points from the data. So it should be similar to the data set, obviously. So you have data set. Now you give weights based on the distance from the chosen point. So you choose a point also. While generating a random point, you also choose a point, which is better if it's in the middle actually. So you give weights from based on the distance from the chosen point. So you can see if it's closer, it is have higher weight, it has higher weight. If it's just farther, it has lower weight. Now these points with these points are now passed to the neural network model, the trained neural network model, and outputs are taken. So now we have a set of new data points, look, weighted data points, and we have outputs from them, which is taken from the neural network model. Now this is used to train an explainable model. So as I told you, for example, let us take linear regression. So this is used to train a linear regression model. So now we got the answer where you can see that. mm, so because this is we are training a linear regression model from the data, from the data set generated, from the synthetic data set generated, we can get the coefficients from the explainable model. This is how Lime works. So I'll just show you a code here. You are declaring the Lime interpreter or explainer. So you're choosing a particular sample from the test set. You're actually creating the Lime explainer. Then you're trying to explain a simple single prediction. Then you use exexp.show in notebook. So show in notebook for this visualization for the output, and you get this. And you get this. From here, you can understand that of that particular 25th index, this is the minimum value that can be, that of this is of the output. This is the maximum value that can be, and this is the answer. This is the actual answer you have. Then you also see the you here you also see the impact of different attributes. You have credit score, income, and years employed, and you also see the coefficients. You have coefficients before, but now you have a Lime value. You have a different value. It's not coefficients to be honest, but you have a different value. This is how Lime works. Next, we'll go to shape. So shape takes uh, inspiration from the game theory to allocate feature importance fairly. Shape is actually short for shapely additive explanations. So each feature contribution to a prediction is calculated based on how the prediction changes when that feature is present versus absent, considering all the possible feature combinations. We have a code here. We just declaring the explainer. You are training the explainer. You are plotting the explainer. You have two plots. One is called the summary plot, and you have the waterfall plot. So here, this is the summary plot. You can see that at the high value of income, the impact on model output is high. So, so this particular, so you can see this last one. So you can understand that as you go down, the distance is being narrowed. This indicates that income is very important compared to the other two. So next comes credit score and years employed when it comes to the importance of the features. Then comes uh then comes the waterfall plot. So you have 78002, which is the answer for your particular point. Uh, so you're taking the 0th and so which is the first tuple of the data set. For that, the answer is been found to be 78K, while the average, over here you can see, while the average is actually 87K, so which is less than average. So why is it actually giving us the answer less than average. Here you can see the answer. So here you can see income, credit score, and years employed. So income is going back. Income is falling on the, what you say, mm, negative region, and years employed is falling on the negative region. While credit score is actually falling positive, but entirely it is falling short. So at last, it's already falling short. The credit score, the positivity of the credit score is falling short, and hence the output is very less. So next you have, let me give you a real world example. So we have XAI financial risk assessment. So imagine a bank using gradient boosting model to evaluate loan applications. So the model achieves good accuracy, but managers and regulators need to understand how decisions are made. So a customer is denied a loan, and both the loan officers and the customer want to understand why. The raw model must output simply provides a probability score of 0.42, which is below the approval threshold of 0.60. But it just gives that. It doesn't explain what why it actually is giving 0.42. That is when XAI is actually used, so that the manager or the loan officer and the customer, they understand why the customer is being denied the loan. How do you implement your XAI in your data mining pipeline? So first you have to define the explainability requirement. So these two parts come under definition and designing, the first two. The third one comes integration, and the last one is explaining. So the first one is you have to define the explainability requirements. What do you need? Are lots enough? Do you need the coefficients? Do you need to understand what? So what exactly are your explainability requirements? So you have to define that. That is the first step. The second step is you choose the right AI tools for use case. So you have to use Sharp, or you want to use Lime, or you have to use something else. Can you use partial dependency plots, or actually you're having a model that's actually integrable. So next you have to integrate XI into development life cycle, which is basically how you're implementing. You're just coding the XI into the development life cycle. The last one is design effective applications. So design effective explanations for your architecture. So first you might have researchers, you have data scientists, you have employees, not employees, you have entrepreneurs who are not in the field of data science. So how do you explain this thing to a researcher? So maybe you can explain him. So if he knows maths, you can just say Shapley values. You can just give him Shapley values and he'll really understand. If you have a data scientist, he might not really understand Shapley values, but you can give him things like coefficients, or you can even give him graphs. Then you have an entrepreneur, or your a boss, who's basically not someone who knows, who's not in the technical side. So for them, you have to give detailed English explanations. So you have to say uh, this particular reason why this thing is happening is because the this particular attribute's value is this. Now let me conclude this by saying that XAI is a cornerstone of responsible data mining, and now uh, explainability is no longer optional. It is explainability is no longer optional. It is essential. It bridges the gap between algorithm complexity and human understanding, ensuring that the powerful insights generated through data mining are transparent, trustworthy, and fair. So, and XAI provides the tools and frameworks to make that future a reality. So we need to so AI. So in the future there might be robots which can actually think and talk, um, and humans. So humans should understand if AI gives particular thinking. If AI says something, humans should understand why the particular AI said it. The AI should be able to say, "I said this. I came to this conclusion because of this." This is why AI is important, and I think XI is important. And XAI is very important not only as a skill. XI is very important as a skill and as a tool for anyone who's getting into the field. So thank you, and XAI is very so thank you. So thank you for watching this video, and goodbye.